Okay, I hope everything is okay and you can hear me. We are going live now here on YouTube. Again, please try and feed back to me if things are not going right. I'll try and fix it as fast as I can. I've got some problems with the chat room, so feel free to try and chat to me. Let me see whether I can see this. So yeah, so I can see the chat room. Somebody type something, please. Okay, right, good. I can see all the talks. Right, I've got a problem with the software I'm using for the PowerPoint. It covers the chat room. So what I'm going to do is I'll press the escape button to go out of the PowerPoint presentation to see what you guys are saying, and then I can return to the presentation. Okay, I'm going to make a start. So what we're going to do is we'll do the same presentation as we did last time round, but I'm going to go through it really, really fast, and then I'll just, where we stopped last time, where we stopped on Monday, I'll just carry on from there. Okay, right. Anyway, it's good to see that you are here and good to see that it's working okay. Sorry for the delay. It's about 8 minutes. I tried to sort the software out, but I struggled. It's beginning, so maybe next time it'll be a bit smoother. Right, okay. I'm going to start off with the slideshow. And right, the second monitor is covered with the software. Let me see, can I get rid of this? No, it's just covered. It's still covered with the software. I can't see anything in the chat room, but when I press the escape button, then the chat room becomes visible again, and we can carry on. Okay, I'll stop sort of every 10 minutes just to make sure that everything is okay. The presentation should last less than an hour, so I'll try to get through it pretty quickly. We started on this on Monday, so it's water cooling systems, refrigeration, 2.6, 2.7, 2.8, and 2.9. A couple of things which we didn't cover, and I just put them into the slides, and I'm going to spend a bit more time on those points. So at the end of the lesson, you will know various methods to cool water, issues related to water-based systems, refrigerator principles, issues related to refrigerants. Okay, we talked about this last time round. So when and where is it necessary to cool things down using water? So we've got the car engine, we've got machines where water is used as a coolant, air conditioning units, power plants, yeah, very, very important. Again, we talked in quite some detail with that. We've got a blacksmith workshop, water to cool down steel when they are working with steel, water cooled going through an engine. And then we've got biological matter as well. So, dogs, cats, humans, we only need water, we perspire to cool down our system, our biological system. And its sole part is as a coolant of some form or another. What are potential problems when using water as a coolant? So we looked at that as well. So we said it's electrics and water. So you've got leaks, conductivity, and potentially short circuits. So that's a problem. Mechanical, when we deal with water mechanical, there's a lot of oxygen in water, and that causes oxidization. So in other words, it's just rust. And that will lead to corrosion, leaks, and scaling as well. Scaling is a big problem. You will find as well when you've got pipes running and there's water going through over time, you'll get limescale building up, and it's a bit of an issue. And then we've got biological issues with water, and again we have to look at this as part of this unit. And it's when you've got cooling systems, you've got water in the cooling systems, there's always a chance of contamination. Water is a substance of life, so bacteria, anything will flourish in water. So it's a breeding environment for bacteria and algae. And algae again can be quite toxic, so it's a problem. Why do we use water? It's cheap, it's plentiful, non-toxic, easily accessible, it's low risk of contamination. Open system for evaporative cooling, it's kind of rubber, anomaly of water, highest density at 4 degrees centigrade. And that's it. Why don't transformers use water for cooling? And again, we went through the answer. There are two issues really. The first one is electrics and water don't mix too well. And obviously, you get a short circuit, you get some water in there, you get some conductivity. But it's actually not quite as size what people think it is. Maybe next time in class we can remind me, we can do an experiment. Just take a glass of water, you can do it yourself, take a glass of water and put a meter in the water and just measure the resistance. And what you'll find is it's actually quite high. It's not sort of 0 ohms or anything like that. If you add some salts and there are some impurities to the water, the resistance goes right down. So you get a couple of ohms. Water could cause short circuits. Water could cause oxidization and corrosion, and with that, obviously short circuits as well. So that's a problem. So anything with water can oxidize, and you get corrosion and rot set in, and that can create a lot of problems. Okay, we looked at automotive cooling. Again, I'm not going to spend too much time on it, but it's just one example where cooling takes place. Cooling and warming at the same time. So you want to get rid of the heat from the engine and cool it down, and you want heat inside of your car. And so you've got like some form of heat exchange taking place, where on one side you take it off, on the other side you want it really, and you put it inside your car. Okay, I'm going to go past it. Right, we've got the next part, which is evaporative cooling. Before we do this, just another look at the water-cooled PC. And that's what they look like. Quite amazing things. I was tempted at times to go for that and try it out, but you can buy kits which cost like about 30-40 quid for a PC. And it certainly looks cool, especially when it's colored water. It doesn't make any difference, not much difference whether it's colored or not, but just looks a bit cooler. We talked about cooling towers at power plants, where water is poured down to cool the steam, which has been used to drive the turbines, and to turn the steam back into water, and to then feed it back into the plant. And now we are on evaporative cooling. So I'm just going to repeat a little bit. I'm not going to spend too much time on it, but just to jog your memory of what evaporative cooling is all about. So again, in this unit, what we are supposed to cover is like these two types of cooling. One is evaporative, the other one is just using a refrigerant. So and a little bit compare them to one another. So again, when we had this, I was asking you to think about summer, think about a hot day, and you swim in a lake and you come out of the water. And what seems to be the case is when it's really hot and there's a lot of sunshine and you get out of the water, it actually feels quite cold. And I don't know whether you noticed this, when you were on the last couple of days in PMC, and you were using the hand gel, for disinfectant. The first sensation you have is it's just really, really cold on your hands. And when you look at what this gel is, it's just alcohol and some other substance to contain the alcohol in there. Now the alcohol evaporates pretty quickly, and whilst it's killing off the germs on your hands, and this evaporation will actually give you the sensation of your fingers becoming very cold for a short moment in time. So they feel really cold and fresh. And that's pretty much the same effect you get on a hot summer's day when you get out of the water. So despite it being hot and sunny, you feel cold. And in contrast, if it's cloudy but you still have got the same outside temperature, it doesn't make that much of a difference. You get out of the water and you still feel kind of warm. Right, more so when it's sunny, less so when it's cloudy. Okay, we said this. And the answer is, when it's cloudy, it doesn't evaporate. The water doesn't evaporate that fast. Or if the humidity is very high, again, the water on your skin doesn't evaporate very fast and you feel a lot warmer. So next time, if you've got a summer this year, try it out and see whether it is so. I'm sure you'll find that it is the case. Okay, but that's all the concept of evaporative cooling. So the hotter it is, the faster something evaporates, the more energy is taken out of it, and the water evaporates, changes state from liquid to steam or to vapor, and that releases. There's energy put into it, into the water, and you will cool down. It'll feel cold. Okay. Next picture, we've got more humidity, less humidity, and again, human body uses evaporative cooling for trying to stay at a certain temperature, to stay cold. So it's one way of doing this. So our bodies always burn lots of calories, and that's one way we keep warm, and we've got body temperature. And it takes, when you go to a hot climate, it takes about a fortnight, roughly about 10 days or so, for your body to switch over, to burn less calories when you come from a cold climate to a hot climate. And also it's interesting, when you live in a very cold climate, like in Scandinavia, people over there tend to have cravings for lots of carbohydrates, which is food, which the body needs to burn off to keep warm. And so there's a certain amount of flexibility to adjust to different climatic conditions within the biology of our body. Right. What else have we got? We've got the body's cooling system. We talked about this, the evaporation and everything. The biggest problem is if we've lost too much water from our body because of compensating for temperature and stuff like that, we can get a heat stroke and obviously dehydrate. So that's a big problem as well. Anyway, we're not talking about this too much. We're just sort of covering the whole idea of evaporative cooling, and it's actually used in your body, and you experience it more or less on a daily basis, to especially in summertime, to keep cool and fresh. And the other thing as well is, if you ever need to cool down because you're really overheating, all you need to do is get some water and splash it all over you. Put some water on your t-shirt or shirt or whatever you've got on, and as it evaporates, it actually will cool you down, and it will be very refreshing. Okay, we had a look at evaporative coolers. So, some piece of cloth. Water is air is blowing through this piece of cloth, and everything cools down. We can have forced convection as well to try and enhance this effect. So we can force air. It's not forced convection as such, but it's forced air. Yeah. So we force air past the the surface which evaporates the water. Could be a piece of cloth or like you can see here. And we could increase the effect and increase the amount of cool air that is generated in that way. So again, evaporative coolers are ideally suited for hot and dry places. So we are looking at the Middle East, or typical places might be in the desert or in a desert climate. Less so in a rainforest. If you're in a rainforest, they don't work very well, and the reason is that the air humidity, is close to saturation. So that means you get close to 100% of humidity, and that means that there's virtually no evaporation taking place, and that system would not work. Right. Let's move on. We had a look at this one as well. So that is the evaporative cooling tower. So again, this one is in Las Vegas, in the United States. Again, the snag is you need a lot of water for that. And when you are in a desert, you don't tend to have a lot of water to play with. But maybe there's some groundwater, they can make use of. That's some of the things they do in the Middle East. Not quite sure about the Nevada. Las Vegas, Nevada, the desert out there, what it's like, but yeah, it's this. So we've got wind catchers, so-called wind catchers in Dubai for evaporative cooling, and this technology again is thousands of years old. Let me just move the mouse. I'm not sure whether you can see the mouse. Here we've got a sort of hacienda-style building complex with a pool in the middle, and the whole idea is that the pool will evaporate water, and as the evaporation takes place, the air around the pool cools down, and cold air obviously stays down. So around this complex, you will have some sort of microclimate where it's very pleasant and very nice to be there. You've got a nice, cool environment near the pool, Whereas if you sort of a common method which has been used in places like Saudi Arabia, the Middle East in general for thousands of years, and also in places like Spain and Rome, where you had these squares with a little pool or water feature inside the square. And the whole idea about the water feature was not, oh, it's pretty and there's some water and the birds can drink, but it's all about climate control, to create these microclimates for people to get some relief from the heat. Okay, next one. We have commercial evaporative coolers. Again, we looked at this on Monday, so I'm just rushing through all this stuff. Hopefully I'm not boring you too much with this. They are commercially available, and as I said before, they are ideal for places where you've got a dry climate, possibly less so in the UK or in these places, but they are available. We've got an evaporator, and you've got a little bit of a fun. It blows air through the through the sheets. In this case, it's wood wool pads, which are filled with water to enhance the whole effect of evaporation, and that will sort of generate cool air. Yeah. So it's a fairly cheap way of running an air conditioning system or unit on a very hot day. Probably more effective and less costly to run than a traditional or conventional air conditioning unit. Okay, the wind catcher, and we can see in Egypt and Persia that's where they use them. When you look at the wind catcher, you can see as well at the schematic here. So you've got air which sort of goes in and is pulled back out again. And so we've got the wind blowing into the wind catcher. It goes down, it goes through the chambers. The water evaporates and it gets back out again, and the whole process cools down the house. So without needing a modern air conditioning unit, you can keep a climate very pleasant and very cool. And that's, again, has been used for thousands of years. I think this was the last thing we looked at on Monday. This is the ancient cooling method. This is like the ancient fridge. So you put all your vegetables in some clay pot, and you've got an inner and an outer clay pot. You put a layer of sand in between, and you fill the sand up with water. Now the water evaporates, and it cools down all the fruit and makes it last a lot longer. So the heat is removed through evaporation, and everything cools down. There's a wet cloth on top of it to keep it all nice and cool. And that's an ancient fridge. I mean, that's been around again for thousands of years. It's just using clever technology, and it's something you can make yourself very, very easily. So if you ever go camping, you just need an inner and an outer pot, put some water in between, some sand in between, put the pot in the sun, and as it heats up, it'll actually cool down on the inside. So yeah. Right, next one. Management of water and evaporative systems. This is a slide which I've inserted. We need to cover this. And what are the issues of using water for cooling? So what are the issues when you have a system like an evaporative cooler, and you might still use them in industry because they're so efficient, so much more efficient than traditional air conditioning units. What are the issues? I'm just going to press the escape button. That means the screen is going to go small, but I can watch your chat. Right. Okay, I'm watching the chat now. What do you think are the issues when you use water for cooling? Did you hear her? Come on, guys. I'm just watching the chat right now. What? Actually, you can see it now, can't you? Because you can see the whole thing. Oh yeah, she just turned up here. Where is she? Oh, she's left again. She was just here to say hello. Water. What are the effects of water? Let me just right. Go back to that one. If you've got water in a system, what Water can run out, so that's one thing. Yeah. What else? Corrosion is an issue as well, especially in industrial system. Thanks, Ryan, for that. Corrosion is an issue. The cost of water supply as well, because you lose water in the process of evaporation. Aaron, thanks for that. Hygiene is a big issue. Yeah. Algae as well, biggie, very very biggie, and limescale. Yeah. So you've got I don't know whether you could read it on the sheet there, but a big problem. Yeah. So you're dealing with. Yeah. When it comes to the exam, I'm not sure whether there's a question on that, but it sounds familiar. So just bear this in mind. So with evaporative cooling, you've got water. Water is a problem. There's algae, bacteria, especially with food production. There's corrosion. It can be acidic. It can be alkaline. Yeah. So there's a problem with that as well. Aaron said Legionnaire's disease. It's a biggie as well. I think we covered it, or we will cover it. I'm not sure, but it's a very big problem as well. So if water is over a certain temperature, Legionnaire's disease can develop. Yeah. And there's this band of temperatures, and we need to keep it either above or below to stop Legionnaire's disease from developing. By the way, Legionnaire's, you can drink it. It doesn't do you any harm, but if you breathe it in, similar to this corona stuff that's going on now, if you breathe in droplets, that's a killer. That's what can give you Legionnaire's disease. It's a bit like flu symptoms. Jimmy, rust, big problem as well. Thank you for that. Rusting is a problem with water as well, especially when you've got it in evaporative system made of steel and metal. Okay, let's go back to the presentation. Right, I'm just gonna slide. Yeah. Come back up with this. So we've got the supply of water. If water is lost as part of the cooling process. Cost of water, bacteria living in water, dissolved solids, salts and limescale. So again, limescale, they can settle down somewhere. So we've got scaling as well. We're going to look later in another presentation at pipelines. Yeah, what we're going to do with pipelines. And scaling is one big problem, and we need to sort of get them cleaned out every now and then. Removal of dirt and solid from water, acidity of the water, pH value, proximity of water to foodstuff. Yeah, so that's a biggie as well. Then we've got temperature issues. We've got water could freeze up potentially. So if you've got a evaporative cooler and you leave it alone in winter time, it might actually freeze up and destroy the thing. Yeah, so that's an issue as well. Buildup of algae, big problem. Right, and that's it. Yeah. Next slide. Refrigeration systems. Need for refrigeration. We've got food preservation to cover the summer period, so that's a biggie. Shipping, scurvy for long journeys, that's sort of a medieval days. Today, obviously, as well, but we've got fridges. The military, very important as well to use refrigeration for keeping food going, and food transportation over long distances. So we've got lorries and things like that. I think we covered this last week as well, on Monday. It sort of reminds me, we've got early attempts where we had ice cellars, we had evaporation cooling, ice houses, winter ice harvesting up to the late 1800s. Yeah. So you had people in places like Canada and I assume here in Europe as well, where they would cut out ice in winter time and put it in a cellar and keep certain places really cool, well-insulated places really cool. Right. Next one, refrigeration research. These are the two guys which were crucial in that. I just wanted to give you an idea of when it all started. So we've got an attempt in 1755 by William Cullen, a Scottish guy, and he boiled ether and could extract heat from the environment. So he created his own small fridge on artificial ice construction. So that's were sort of first experiments in the 1700s. And to be fair, a lot of stuff was done then. They were messing about with electronics and electrical. Oh dear. She's not understanding why I'm talking in this microphone and not to her. Don't know whether you could hear. That was Cleo. So we had Benjamin Franklin and US founding father, the guy with the kite and the key, who almost electrocuted himself, and he did some experiments with alcohol. And then first vapor compression was done in 1834 by Jacob Perkins. And then in the 1890s, refrigeration was widely used in the food industry. And then home use was 1920s to 1930s. Yeah. So just to remind you, I think we covered it on Monday, but here we go again. The compression cycle. So I'm going to spend a little bit of time on this because that's important. So when you walk away from this presentation, you should, number one, know is there's evaporative cooling and there's cooling using refrigeration. And and this is a refrigeration cycle, or the vapor compression cycle. And you need to get this in your head. Yeah, that's very, very important. For the exam as well, I think if I remember right, there's one question where you need to explain this. Yeah. So the vapor compression cycle is used in most household refrigerators as well as many large commercial and industrial refrigeration systems, or air conditioning systems for that. It's the same thing, it's just exactly the same thing. And in wintertime, you just turn it around. Yeah, so the cold goes outside, the heat goes inside, and in summertime, the cold goes inside, the heat goes outside. So in figure 1, we've got vapor compression, refrigeration, and thermodynamics of the cycle can be analyzed, shown in figure 2, which is temperature entropy diagram. So we've got the upper diagram and the lower diagram, and what we get here is we've got saturated liquid and we've got superheated vapor. And then we've got this bit in between where you've got a mix of liquid and vapor. And that's pretty much what's going on inside your fridge. Okay, I'm going to go through the slides and it sort of explains it. I will, because of everything that's going on with Corona and stuff like that, I will upload the presentation or make it available to you, so you don't have to worry about taking notes. Yeah, so makes it a bit easier on you as well. Right, from point 1 to point 2, from the fridge side, from the cold side, and the vapor is here. So it's compressed, and with that. We've got a condenser on the other side. It heats up, and the vapor, with the pressure, because it's pressurized, turns back into liquid, through the condenser. So again, vapor has got a higher energy state than liquid. That's what we have learned through, the MUD Australian professor. So per gram for water, it's 540 calories. So the energy is released, so the vapor turns back to liquid, and so energy is released. And what you find is, down over there you can see the mouse. On this side here, you've got heat building up. On this side here, you've got heat building up, and that is basically the energy being lost in the process of turning this from vapor to liquid. Okay. So down here we've got liquid again, and I think that's the next stage. So when we look here, so we've got the vapor. Where's the vapor? Vapor is on this side here. And so we are moving it over to that side here. So we are at 1. So we heat up the vapor. Then it goes down to 3. Yeah. And again, we're going to go to the next slide, and it should make more sense. So from point 2 to 3. So we've got point 2 to 3. You can see this here, point 2, point 3. I hope the mouse comes through on the talk. And on to point 4. So we go on to point 4. So the vapor travels through the condenser, which cools the vapor until it starts condensing. Then the condenses the vapor into a liquid by removing additional heat at constant pressure and temperature. Yeah. Okay, so that is the thing. Right, next one. Between 4 and 5, so we've got the saturated liquid here. Between points 4 and 5, the liquid refrigerant goes through expansion valve, so also called a throttle valve, where pressure abruptly decreases, causing flush evaporation and auto refrigeration of typically less than half the liquid. So that's the expansion valve here. You can see this there. And we're going to go into this region here. So if we're going to go from 4 to 5. So we've got a mix of liquid and vapor. And that is sort of where we've got the cooling side here. So if it were an air conditioning unit, we would have warm air coming in, cold air comes out. If it's a fridge, it would just cool the whole thing down. And yeah, that's what it would do. Right, next one. that's we're going to number 5. So the results in a mixture of liquid and vapor at a lower temperature and pressure shown at 0.5. So that's down here on this diagram. Yeah. So it goes from one shape to another, and energy is, released and put into it, and so on. So the cold liquid vapor mixture then travels through the evaporator coil or tubes and is completely vaporized by cooling the warm air being blown by a fan across the evaporator coil or the tubes. The resulting refrigerant vapor returns to the compressor inlet at 0.1 to complete the thermodynamic cycle. So that is the compressor inlet here, and then the whole thing starts again. So we pressurize the thing. It's a lot of energy released. Yeah, turns back into a liquid, and then there's this valve here, and it sort of turns back into no, it doesn't turn back. It turns into a vapor. Yeah, and so we've got. Then from the vapor, it turns cold. It takes energy out of the system as it turns into a vapor. So that's the reason why it gets cold. And then we put it back into a compressor. Right. I hope I've explained it reasonably well. I'm just going to press the escape button so I can see the chart. And are you okay with everything? What we were talking about so far? Do you understand the compression cycle, or? Right, I can see there's a little bit of a delay here. I'm just waiting for a bit, and I've got a cup of coffee. Are you okay? Just give me a thumbs up or something if you're okay with the compression cycle. If you've got any questions, let me know, and then I can sort of go through it one more time if you want me to. Okay. Okay, that's good. Okay, thanks for the thumbs up. I can see them. Okay. George is asking, will this be on YouTube after we finish work? I tried it once and it worked, and I tried it another time and it didn't work. But I'll try to put it on YouTube. Yeah, I'll try to put it on YouTube. So, there's some problem with YouTube. If you miss one setting or something, it just deletes it and it's gone. And this is what happened before. But I'll try to put it on. Okay. Right. I'm just gonna go on. I need about, what's the time now? I need about 10-15 minutes and we are done here. Okay. 10-15 minutes and we are done. Any questions, Fash? Any questions you have, particular? Okay, I'll move on. Fash, if you want to stay behind, we can go through some of the bits again through the refrigeration cycle. Okay, I'll go to the next slide. Right, let's quickly go through this. We've done this, We've done the compression cycle. Okay, I'm gonna go through that. You've got the compressor down here. This is the condenser. And then the evaporators on the inside. If things go wrong with the fridge, it's either that the refrigerant is no longer enough in there, so it's been leaking out. There isn't enough air for the condenser to get rid of the energy of the heat which is produced. Could be an electrical fault with the compressor, or it could just be that the pump is worn out. Yeah. The compressor is just a pump, really. It's nothing else. Okay, refrigerants. Substance mixture, usually a fluid used in a heat pump and refrigeration cycle. It undergoes phase transition from liquid to gas and back again. Fluorocarbons, especially chlorofluorocarbons, became commonplace in the 20th century, but are being phased out because of their ozone depletion effects. Other common refrigerants used in various applications are ammonia, sulfur dioxide, hydrocarbons, such as propane. So that is the thing. So at the moment, we've got the problem with ammonia as toxic, as is sulfur dioxide, and hydrocarbons such as propane, they're explosive. Yeah. So that's always a problem with refrigerants. You can see a couple of them here. We've got water, we've got methanol, benzene, acetone, and you can see all the critical temperatures. The ideal refrigerant needs to have a boiling point that is somewhat below the target temperature. It's got a high heat of vaporization, a moderate density in liquid form, relatively high density in gaseous form, high critical temperature, should not be toxic, should not be explosive, and should be environmentally safe. The CFCs, they fit all of these apart from being environmentally safe, but when they came out, they didn't really realize what they were doing. And so they've been replaced now, CFCs. Most promising alternative is CO2. Carbon dioxide is non-flammable and non-ozone depleting. It can be used as a working fluid in climate control systems for cars, residential air conditioning units, hot water pumps, commercial refrigeration, and so on. This is what we didn't look at last time round. These are all the maintenance aspects. So what can happen with a fridge? This is a big question, and maybe for you as well. What is the stuff you can realistically do to try and fix a refrigeration system? So if a fridge goes down, first I would try and see whether the pump is actually working. Does it make some noise? If it doesn't make noise, there's a good chance that there's an electrical fault, or maybe the pump itself has gone down. Inside that bearing is gone or something, that is mechanical fault. If the pump is working, then a chance could be that the refrigerant is leaking. And if the refrigerant is not enough or not sufficient, and it can't pressurize sufficiently, what you may find is that the inside of the fridge gets warm as well as the outside. Yeah, that it doesn't, the whole process doesn't work anymore because the pump can't build up enough pressure. Right, failing expansion valve. Compressor works, no leaks. Could be possibly the valve, but they are unlikely to break down really. The thermostat could be wrong. So if it over freezes or doesn't freeze at all, so it could just be that the thermostatic control is gone in the refrigeration unit. So you can do a resistance test to make sure whether they work. Maybe just change them over, manually override the thermostat and see whether you get the fridge to work one way or the other. Lack of ventilation for the condenser is a big problem as well. So if you find that the condenser is like dusted up and air can't go around freely, the performance and the efficiency of the fridge goes down. Also interesting as well, the more ice builds up on the evaporator, so that's a bit inside the fridge, the more energy is necessary as well. And it can be that the condenser overheats because there's too much ice on the elements inside the refrigeration unit. So all you have to do is just de-ice the evaporator, just turn it off, get the ice off, and then turn it back on again, and that's all you need to do in that instance. By the way, it's also a little piece of advice for home if your electricity bill is fairly high. Check your fridge and see whether it's all iced up. If it's iced up, knock all the ice out, de-ice it, and it'll be okay. Electrical faults, obviously check fuses, wiring, and the power unit itself. And there isn't much electrics within refrigeration other than the thermostatic control and just powering the pump, and that's really all it is. Yeah, it's not much to it. But again, it can go faulty. It can just be a dodgy contact or a fuse that's gone or something like that. Right, a little bit of a quiz. I'm going to leave it up for a couple of minutes and then I'll go back to the chat. Name 2 main ingredients for evaporative cooling. In what type of climate would evaporative cooling not work at all? How did people in ancient Egypt keep their fruit cool? How could you improve the effect of evaporative cooling? Name 3 issues you would have with water used for evaporative cooling. What are the 2 phases of a refrigerant in the cooling cycle? So again, a bit of thermodynamics here. What is the purpose of the compressor? What happens when the refrigerant goes past the expansion valve? The 3 potential faults you could have with a refrigeration unit. Right, if I can ask you to, each one of you, to answer 2 of those questions quickly, and then we are done for today and I can release you. I'm just going to go back to the chat room. Okay. Right. I'm just looking at the comments. I'm going to go through the refrigeration unit one more time. Yeah. And Sarah, yeah, by the looks of it, we'll be doing these sessions more often because of Corona. And I think the cat's very happy as well. She's just sleeping right next to me. She likes this sort of setup. Okay, I'm going to go, right at the end, I'm going to go one more time through the refrigeration cycle. It wouldn't work in the Amazon, yeah? Spot on. Water and heat, okay. That's for question number 2 ingredients of evaporative cooling, okay. 3 pot in the pot cooler, yeah, that's good. Thank you, Sarah. Okay, have you got some more answers? Why wouldn't it work in the Amazon? Quick question, Joe. Okay, to pump refrigerant round. Okay, but what else is... it's important that we have a compressor and that compression actually takes place. That is not just about the pumping action. If we pump it around, nothing would happen. We need one other ingredient for that. Josh, can you elaborate on that? Bacteria scaling mechanical issues from oxygen in water. Yeah, thanks, Aaron, for that. It's too humid, okay? Yeah, that's the thing. Evaporative cooling doesn't work if there's a high level of humidity in the air, and it's a problem. Number 4, 1, 2, 3, 4. Use for evaporative cooling. Okay, thanks, Natasha. It would run out corrosion, legionnaires, lime scale, pH, etc. Yeah, spot on. Thanks for that. Okay. One more. Give me one more answer. I'm not sure whether we've covered all. And then I will officially end the session and go one more time through the refrigeration cycle. So you can stay if you want to. Or I know you're about to call it a day, I think, wherever you are at the moment. Ruana, the last one, that could be dirty coils or leaks in the system. Yeah, okay, so coils as well, dirty coils. Leaks in the system is a biggie. Yeah. So, the condenser coils at the back, yeah, if they get dirty, it's a problem. Okay, Josh, when it's pressurized, heats the coolant up a bit, allowing for it to cool after expansion. Okay, that's spot on. Yeah, thank you for that, Josh. Spot on. Okay, first of all, I want to thank you for coming online. We've had about 15 people I can see now, so I think it's almost a full class. Please let the others know as well. I had a couple of emails bouncing back, but I can see you, those who bounce back. Anyway, thank you very much for coming online. We'll carry on. I'll send you an email with a link. I think it worked okay with, there's a little bit of a delay I can see, but it worked okay with YouTube, so I'm probably going to stick with this method. And I will try to record this session or keep the recording going and upload it. And you can go through it one more time. So I will officially release you at this point. So if you need to go, feel free to go. I'll go one more time through the refrigeration cycle, and then I will say the final goodbyes and wish you a great day. Okay, let's go through the refrigeration cycle one more time, and then we are done here. Feel free to stay if you want to, or if you need to go, you can go. Okay, so I'm just going to go through those slides here. When you just follow the mouse, when you look at that thing here, that's the refrigeration cycle. So we've got a compressor here, which is just a pump. That's all it is, just a box standard pump. But we've got an expansion valve here, so some pressure builds up behind this valve, which means the whole system on this side here builds up a lot of pressure. So we've got the vapor coming into the compressor. And again, remember when we turn vapor into liquid, we lose energy. So that's the reason why we get heat released from this process. So the vapor turns into, is pressurized, and as the vapor pressurizes, it goes through the condenser. The condenser in turn will lose a lot of heat, and so we release the whatever calories it is for the refrigerant of energy through this condenser, and it slowly turns into a liquid. So we've got the valve here, and the valve again, pressure builds up behind the valve, and on the other side there's a low pressure. So with this low pressure, the liquid can vaporize, and in order to vaporize with this lower pressure, it needs to absorb energy. It needs to absorb energy. So we've got warm air. So this is the calories, the energy which we need to turn this from liquid to vapor. So this goes past the evaporator, and we get cold air coming out of the evaporator, and then the whole thing from a liquid vapor turns into just fully vapor, and then by the time it gets back to the compressor, it turns back into slowly into liquid. It gets pressurized, and then goes through the condenser, turns into a liquid, and so on. And so we've got this circle, this where it goes from vapor through the condenser to liquid, low pressure area here on the other side, and then we've got liquid vapor, and it goes through the evaporator, and energy needs to be put in there to turn it into vapor. And so this energy is taken from the environment, and we get cold air coming out of it. And when you look at the diagram down here, just below here, you can see all the different points. So we go from point 1 to 2 to 3, and then it turns back into a liquid vapor, and we've got a liquid. And so it just goes to and fro on this system. Okay, that's it. I'll just go back to the chat room. Right, we are done for today. And I'll anyway, have a great day. I'll see you tomorrow. I sent you an email before, so to give you some warning, I'll send you an email about 1 to 2 hours before the session starts. So I just need to make sure that everything works. I want to improve a little bit on the system so that I can see you chatting whilst I'm doing the presentation. Okay, have a good evening, and stay healthy and safe, and I'll talk to you tomorrow. Bye-bye. Okay, you're welcome. You're welcome. Thanks, you too, Aaron. Have a good evening. Sarah, can you just email me your college account? I haven't got it. It's gonna take me ages to find because I've just got the web interface. Can you email me? I tried the email you've written down and it bounced back, so I'm not sure what was wrong with that. Okay, thanks, Sarah. Okay, Joe, you said what time will the lesson be? I don't know whether you're still here. I'll send you an email about 8:30, 9 o'clock. That's sort of my plan at the moment. And then what I need to do is the problem is I haven't got the software I need, so I need to turn the presentations into presentations. The presentation that's already been made for Open Office. Yeah. And sometimes it works and sometimes it doesn't very well, so I need some time to fix them. So I'll plan sort of to do it about 11ish, maybe just before lunch, 10:30, 11. So that's the plan so far. But wait for the email tomorrow. You need the link anyway. So okay, Tom, I'll do that. I'll do that. Okay, what I'll try and do is I'll try to have the presentation unlisted because I think the chat is visible. And I don't want the information to become public, but I'm going to send all the links out to you so you can go through the presentation again at a later stage. But only you will have access and whoever you give access to. Okay. Right, okay. Any more questions? I'm just going to wait a minute or so and then I will end the stream and let you all go. Okay, I will end the stream. Feel free to email me if you've got any further questions. So it's mschomborn@kirkleyscollege.ac.uk.